All right, team, it's time to start talking waves. Most of this you're going to find is review. You're going to get one, maybe two totally fresh equations, but one of them you've actually seen before in the lab when we did flying pigs. So we're going to talk a little bit about what a wave is, what an oscillation is, and what the basic definition is of simple harmonic motion. And you guys are going to get some old terms that you're going to be able to organize into a new way, and you're going to get some new terms and a couple of, like I said, a couple of new equations. Vast majority of the equations are old. Some of them are really old. So let's get started. So we're going to start first about talking about what an oscillation is. And an oscillation is something that moves back and forth in a repeating motion. So I want you guys to think in your mind right now. Just take a minute, hit pause. And I want you to think of something that moves back and forth in a repeated motion. Try to come up with maybe like, I don't know, 3 or 4 examples of things that move back and forth in a predictable way. So on your mark, get set, go. Hit pause. Try to come up with them yourself. If you didn't hit pause, I'm telling you, you better hit pause and try it. I'm going to do this whole time. Make sure you guys are working out those examples on your own first. So here's some examples. Things like tides. Walking would be considered an oscillation because your legs are continually moving back and forth. Your heartbeat would be considered an oscillation. All sound waves are oscillations, which we're going to explore a little bit later on in this chapter. Clocks are oscillations, both the hands on the clock that go around on an analog clock. And also, if you think about grandfather clocks that have the pendulums on the bottom that move back and forth, vibrating atoms, guitar strings, circuits, light waves, all of these things move back and forth in a repeating motion or in a predictable pattern. So this concept of simple harmonic motion, as a rough definition, we say that it's the time that's taken for each oscillation is the same regardless of the starting position. So if you think back to your lab that we did on Friday, your power lab that we did with the pendulum, you realize that the only thing that impacts the period of a pendulum is the length of the string. So when we say regardless of the starting position, we're saying it doesn't matter what angle you release that pendulum from, you're going to get that same back and forth motion that can be timed, that each oscillation is the same. So we call that term, when the time that's taken for every oscillation is the same, we call it isochronous. So those are all events that occupy equal time. So if the motion is repeated and it's isochronic, or isochronous, sorry, not isochronic, we call that simple harmonic motion. So it's basically just a fancy way to say something that moves back and forth in a repeated and predictable way where every time interval is the same. So we're going to see lots of examples of that. We're going to see kind of some weird examples of, masses on springs, that sort of thing. Physics loves using masses on springs. And we will see lots of things like pendulums and even things like that move in a circular motion. Those are also simple harmonic oscillators. Things like record players and CD players and stuff of that nature. So moving on from there, we're going to hit up some pretty much basic review terms. Let me get some of this covered up so it doesn't make you panic. So an oscillation occurs every time something is displaced from an equilibrium position, and then that experiences a restoring force. So something that pushes or pulls it back to where it came from. So if you think about equilibrium position, I like to think, in terms of oceanography, I like to think of waves. So that equilibrium position out on the water would be like being on the ocean when there's no waves around at all. And then the big thing that pushes those waves out of equilibrium would be the wind. So wind is what generates waves. And that restoring force, that thing that pushes or pulls those waves back to where they came from, is gravity. So that would be an example of taking an equilibrium position and then trying to move something away from that equilibrium position and then through a restoring force. So the definition of an equilibrium position is that spot where no F net, no resulting force is acting on that object. So in other words, where would that object be if you just let it do its thing. In terms of, for example, say a pendulum, that would be the pendulum. Once you hung the pendulum off the spring like you did in class, and you just, or off the apparatus, and you just let it hang there, and you didn't disturb it at all, and it just hung there on its own, that was that pendulum's equilibrium position. Then you took that mass on the end of that pendulum and you pulled it back, so you disturbed it. And then there was a restoring force. That restoring force in the pendulum example was obviously gravity. Gravity was trying to pull that pendulum back to its equilibrium position. And the pendulum started swinging because the restoring force did a really good job at, in fact, it did such a good job that it happened in both directions. So in other words, that pendulum swung one way and then it hit the equilibrium position and it actually swung. So we pulled it back, it hit that equilibrium position and it was like, whoops, too much. And it actually swung through that equilibrium position back to the other side. And then gravity pulled it back this way and whoops, we went too far and whoops, we went too far. Now with our pendulum in class, obviously over time, we're going to have things like friction, and that sort of thing, eventually get that to come to a stop. If it was a true simple harmonic oscillator, it would never come to a rest position. It would continue to move back and forth. And really to get a true simple harmonic oscillator, it's not easy to do because there's always some sort of outside force acting on things, but we can, we give it a shot. And if we can set up an equation or we can set up a system well enough, we can get things to where we say, yeah, that's pretty much basically a simple harmonic oscillator, or this is having simple harmonic motion, and we can go from there. So here's an example of that pendulum. This would be the pendulum in its equilibrium position, and then you pulled that pendulum back at a certain angle out of that equilibrium position. The restoring force, gravity, is pulling it back towards position 1, but it swings past position 1, it goes all the way up to position 3, and then that restoring force acts again, and it goes back to position 2, so on and so forth. So hopefully you guys get this idea of this, this back and forth motion that's really predictable. And so now what we're going to talk about is what we need to discuss when we're talking about these oscillations. We got to ask two things. Number one, we got to ask, how large are the oscillations? And so in other words, what is, and we'll talk about what that term is in a minute. You might ahead of time recognize that as amplitude. And also, how quickly does it oscillate? In other words, what is that object's time period? How long does it take to go from this disturbed position back to this disturbed position again? So those are the two big questions that we ask. We say, how large are the oscillations? In other words, how much energy are we putting into the system? And number two, how quickly does it oscillate? What's that time period? Those are two things that we really need to have a good grasp on when we're going to be talking about oscillators, because those things can change pretty frequently, or those change as we change the system or we change the setup. So here's some key terms for our equations. The first thing, and you guys, these are not really new terms at all. Maybe amplitude is a new one. So our new key terms, or old key terms, displacement. So we're back to our friend displacement again. The only difference is that this time, instead of using S like we do in linear for SUVAT, we say X. So it's a distance in a specified direction from the equilibrium position. We measure that in meters. It varies continually. So in other words, that displacement over time is going to change as that pendulum moves through this motion. That displacement is always, always, always changing. But the nice thing is that it does change in a really predictable pattern. The farthest point that it displaces from is called the amplitude. It's that maximum displacement from the equilibrium position to the furthest point of travel. So we say that if you have the larger the amplitude, the more energy you're putting into the system. So I want you guys to think about it. If you're going to give a really big displacement all the way up here, you're adding more energy to the system because you're adding potential energy. And as it swings through, that's all going to convert to kinetic energy, as opposed to only bringing it up to, say, here, for example. So the larger the amplitude, the more energy is getting injected into that system. Now, we sometimes use the phrase, or we use the letter capital A. You'll see that time and time again, or from time to time. But more specifically, we use this term X with this little zero down here. We call that X naught. So x naught, and then negative x naught would be that opposite direction or that opposite maximum displacement. So in other words, we would say that this position 2 here would be x naught, and maybe position 3 over here, since we're moving to the left, we call that negative x naught. So that represents that maximum displacement. We have to find a marker in our equations to talk about maximum displacement. So that's why we have this little subscript here, because this again is always varying. Couple of reruns. We've got period, the time for one complete oscillation, capital T, measured in seconds. Sometimes we call it a cycle. So you could hear it termed as a cycle, or you can hear it termed as an oscillation. You'll hear me use oscillation a lot now that we're starting to talk about simple harmonic motion. And frequency, which is the inverse of the period. So this is seconds per oscillation. This is cycles or oscillations per second. Again, we measure frequency in hertz. You will often see things as kilohertz, as megahertz, or gigahertz, as 10 to the third, 10 to the 6, 10 to the 9. Don't forget that those terms are in your packet that you get for the IB exam. So don't feel like you have to memorize mega and giga. But honestly, guys, we run into these terms all the time, so it's not gonna hurt you too much to start remembering those in your head, so that you can automatically just throw those powers on and know where you're headed in an equation while you're trying to work some things out. So we're going to talk real quickly about two oscillations. So let's say we have 2 kids on a swing set, and there's 2 kids that are swinging back and forth. If they are swinging at the exact same displacement at the exact same time, we say that they are in phase, or they are exactly in phase. If they're not, we say that there's a phase difference. So if they say that if one kid, whoops, you can't see that, my bad. Okay, so if two kids on a swing set, if both of them are coming to that forward position together and both of them are coming to that back position together, we say that those 2 kids are in phase, or those 2 oscillations are in phase. Sometimes if you look at kids on a swing set, you got like one kid who's like too afraid to go too high, or maybe they start at different times. Maybe one kid is totally forward while their buddy is all the way back and they're doing one of these numbers. That means that there is a phase difference. If they are perfectly opposite, behind by exactly 1/2 of an oscillation. So, if my hand is Timmy and my pen is Judy or whatever, and Timmy's all the way up to the front of the swing set and Judy's all the way to the back, and they're passing perfectly through here, and now all of a sudden Judy's all the way in the front and Timmy's all the way in the back, and they are continually moving back and forth, we call that exactly out of phase. We're going to be talking more about this later. It starts to play a pretty big role when we start talking about things like diffraction. So I just want you to have this on your radar as we're starting to talk about waves, because as soon as waves start traveling, we get into this concept of phase difference. So I just need you guys to understand what that means. It just means that if you've got 2 waves and they're separated by each other by just a little bit, we consider it a phase difference. So I want you guys to set up a couple of conditions for simple harmonic motion before we move on and start working on some practice problems. So if we look at what the conditions are, in other words, what do we need in order to get simple harmonic motion to occur? And so what's actually happening, and I kind of touched on this a little bit, is we say that the simplest oscillation will occur. We're going to start to get some numbers on this. So the simplest oscillation will occur when an object, like a mass attached to a spring. So let's say we've got, rather than our pendulum being attached to a string, now it's attached to a spring, and we give that mass a little pull, and we pull it down towards the earth, and then we let it go, and it starts going doing back and forth, right? That would be an example of simple harmonic motion, because there's an object like a mass that's attached to a spring. It's getting pulled away from its equilibrium position, and then it experiences a restoring force. That restoring force has to meet 2 conditions in order to be simple harmonic motion. The first condition that it has to meet is that it has to be proportional. That restoring force has to be proportional to the displacement, and it has to be in the opposite direction. So if we think about our spring and a mass on our spring that's getting pulled down and doing the little doing thing, if we've got this mass, so I'm going to draw this here. Let's say we have a spring here. Actually, I should make it probably look sort of like a spring. And we have a mass on the end of the spring. And we're going to say that this spring its equilibrium position is right here. So if we were to just leave this mass on its own, this would be its equilibrium position. This is where it wants to be if nothing's bugging it. Okay, so we're going to take this mass and we are going to pull it. And so here it is in its equilibrium position, and I am going to pull it at a certain displacement. Okay, there is energy stored in that spring. If you guys remember, that would be that spring constant, right? So there is that energy that's kind of wound up in the coils of that spring. So as soon as I let this guy go, what's it going to do? Well, it's going to try to go back to its equilibrium position, but it's not going to do just that equilibrium position. It's going to go past that equilibrium position. So it undoyoyoyoings, and it's going to come back up. It's going to be more scrunchy up here. So it's going to come up above this equilibrium position. So this would be our maximum displacement on this end. That would be our x naught, our amplitude. And then it would come up, if it was a simple harmonic oscillator, it would come up exactly to that opposite displacement on the other side. So it's proportional to the displacement, but that restoring force is in the opposite direction. So in other words, the displacement's going this way, but the restoring force, that spring constant, that tight wound coil of that spring, is pulling it back this way. So it's opposite. Then once we get here, if we think about this, once it hits this point, it's not going to stay here. Why is it going to come back to that equilibrium position? Well, now gravity is going to be acting as that restoring force. So you've got this motion, this displacement going this way, but the restoring force moving proportionally in the opposite direction. So if we try to kind of nail that down in numbers, we say that force is proportional to the opposite of that displacement. Or we could also say that the acceleration is opposite to that displacement, because that force, because those forces are also related to the acceleration. So again, why is that value negative? Well, because it's forces, and forces are vectors. So that force is applied in the opposite direction to the displacement. So this is a big concept that we're going to have to really remember, especially when we get to, there's a little bit of a funky equation that we're going to see tonight, that you have to remember that force is opposing the motion. So these two equations, that acceleration being proportional to the negative displacement, that force being proportional to the negative displacement, I want you to hold that into your head for later. So this is called simple harmonic motion, and it's determined, or it's defined, or we define it in terms of acceleration. But acceleration is proportional to force, so the relationship's the same. So basically, as I said before, that restoring force is acting kind of opposite. So I said that one way, but then the equation got written backwards. That force is proportional to the negative displacement. And then we know that, like I said, or as I said before, we define it in terms of acceleration. So even though we say that even though we're looking at forces, really mathematically, we most often work with those accelerations. And so that acceleration is proportional to force, so that relationship remains the same. So that acceleration is always directed to the equilibrium position and in the opposite direction. So this is, if we put this on a little graph and we graph our displacement, we have our maximum displacement over here, and we have our negative maximum displacement over here, so x naught, and we look at our acceleration. The acceleration is always directed to the equilibrium position and in the opposite direction. So in other words, this is going towards the equilibrium position and in the opposite direction. And then once we hit this point here, it's going back towards the equilibrium position and in the opposite direction. So this is just a really oversimplified graph. But if you remember back to our spring days, with our kinetic energy of a spring, if you're noticing, it is very, very similar to a force versus displacement graph. And again, the slope, this K, becomes that force constant. So if we could calculate the slope of the line, if we go back to our spring example, we would know what the spring constant was. So that is the basics for simple harmonic motion. In the next video, we're going to talk a little bit more in depth about it. We're going to relate it to the period of a pendulum. And we're going to get a couple new equations in that we will go in depth with a little bit later on. We'll get some practice. So review your terms, try to get really comfortable with what you've just listened to, because you haven't really had any examples to work out, but just try to get comfortable with what you're listening to, because we're going to start applying it mathematically in the next video.